All right, so my goal for this question is going to be to show as little work as possible, not because I hate work. Uh, it's more so just because a lot of this is just conceptual. You just got to know how it works. And it's not too hard, so let's dig into it. We have to find the voltages and currents for both the capacitor and the inductor at 3 different times, right? So let's just dig into it. The first thing you should notice is this right here. Now, this is a little funky looking, but we can kind of just think about it logically and try to figure out what's going on. So we have stuff happening at t equals 0 and t equals 5, right? So let's just draw those out. T equals 0, t equals 5. So we start out at what? 0 volts, right? There's nothing before this. Okay. Then we jump up by 5 volts. So we're going to jump up to 5 volts over here. And then we jump down by 3 volts. So we're going to go down and we're going to be at what? 2 volts now, right? So this is what's happening to our voltage over time. That's what we can figure out from this. Okay, cool. So what do we need to find first? Well, we need to find everything from the negative side of 0, right? So how do we do that? Well, here's 0 right here, and we need to find out what's going on here. Well, as you notice, we have this stretching into, so we have it be 0 volts stretching out for millennia and millennia, right? So we can just assume that we're in DC conditions right now. And since we're in DC, the capacitor becomes an open circuit, and the inductor becomes a short circuit, right? So there's our new circuit now, considering that we're in DC. This also, we know we're at 0 volts right now, so let's replace that with 0 volts. Okay, perfect. So what does this tell us? First of all, there's 0 volts, so nothing is happening in this circuit. There's an open circuit here, so there's no current. There's 0 volts, so there's no voltage. So literally everything's dead, so let's just write that down. Boom, 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 everything's dead. Okay, kind of depressing, but let's see what happens next. Okay, let's erase that. Now we're in the positive side of 0. So we're still very close to 0, but now we're right there. Okay, so what do we know? Well, now the voltage is 5, right? So let's write that down. 5 volts. That's where we're at right now. What else do we know? Well, we're not in DC conditions anymore, so we can't just like cancel these out anymore. We got to think a little more. So we're at 5 volts. What do we know about capacitors and inductors? Okay, here's what you need to know. And write this down in your cheat sheet if you have to. Capacitors can't change voltage instantly, whatever. So capacitors cannot change their voltage instantly. What does that mean? Well, that means that it takes time for the voltage to change, which means right before 0 and right after 0. So in an instant, there's not going to be any voltage change. And inductors are the opposite. They cannot change their current instantly, right? So right before 0 and right after 0, the current is going to be the same. Okay, cool. So now we have those two down. What does that tell us about the rest? Well, we just said that this is equal to 0, right? And since this is a series circuit, that means that all the currents are equal to 0, right? So any current going into here also has to be equal to 0. So we can just write that down right here, 0. But what do we say about voltage? Well, we can't say the same thing about voltage, right? Voltage doesn't care series or whatever, right? We have to think a little more about voltage. So let's break it down. We have 0 amps going across this resistor, right? 0 amps going here. We have 0 amps going across this thing, right? So for both of these, there's 0 voltage drop. For the capacitor, VC is equal to 0. So that's how we know there's no voltage drop across here. There's 0 amps, so there's no voltage drop across here, right? So since we know there's no voltage drop across both, let's just replace both of them with a short for now, okay? So there's no voltage drop there. Let's throw a ground in here, right? This is 5 volts. This entire node is 5 volts. This entire node is ground. So positive, negative here, this has to be 5 volts, right? Again, this and this are the only two things in the circuit right now that we care about. So we can just say this is equal to 5 volts. Okay, perfect. Now we're at our last state. So let's erase and redraw stuff. What do we know now? We are going to infinity, right? So now we're on this end. We're going on. It's been millennia and millennia. We're going to infinity. What's the voltage at? 2, right? 2 volts. Okay. What do we know going to infinity? Again, we're going on to infinity, which means this becomes an open circuit again. This becomes a short circuit, right? Open This becomes short. What else do we know? Okay, so this is open, which means this voltage is gonna, there's not gonna be any amps going across this, which means there's not gonna be any voltage drop. So we could even represent that as a short circuit. And for our purposes. All right, so we know that there's 0 amps going down there, right? So both the amps are going to be 0, just like that. And we also know that across the capacitor, there's going to be, there's going to be 2 volts at this point, right? If we had a ground in here. And we know that there's going to be 0 volts at this point, right? So 2 here, 0 here, which means that the voltage across the capacitor is going to be 2, right? This is a short over here, so across this short, there's no voltage at all. So this is also 0. And yeah, there is our final chart. All right, so for part B of this question, now we have to find alpha and omega naught of the same circuit, right? Now, one thing that should immediately stick out to you is that this is just a simple series second order circuit, right? We got a resistor, a capacitor, an inductor. Perfect. This actually matches, these are flipped, but that's fine. That doesn't matter. We still have this circuit pretty much. So what we can actually just do is use these equations. We can use these equations. So for alpha and omega, we just need these two, right? So let's just plug into those. Pretty straightforward. It's just, can you use your calculator, right? So alpha, according to our cheat sheet, was equal to 2RL, right? Which is equal to, what's our resistance? 10 ohms over 2 times 25 nano. What is this equal to? 2 times 10 to the 8s minus 1. I didn't do this in my head. I had that written down because I've plugged it in already to my calculator. Same thing with this one, 1 over LC. That's just square root 1 times 25 nano times, 1 nano? Which is equal to 2 times 10 to the 8s minus 1. Immediately, we notice alpha and omega, they're the same thing, right? According to our cheat sheet, since they're the same thing, that means we are critically damped, right? So let's go back and circle that. Critically damped, we can even write in these values now that we know them. All right, so now we're almost there to the end. Last question. Now we have to find VC of t for all time t, right? So we already did half of the work. We already know that we're critically damped. So I'm actually going to go over to the other cheat sheet because this one helps us out more. This gives us our golden equations to solve this quite simply, right? So we know our final solution is going to be in this form. So let's just go ahead and write that down. VC of t is equal to B1 plus B2t e to the negative alpha t plus BC to infinity, right? And this is all wrapped in a unit step function. All right, so what do we have to do? Well, first of all, we have to find out B1 and B2. But before we even get there, here's one thing I want you to keep in mind. Whenever you're trying to solve a function and it's in this form, like a unit step form, there's something else you need to do. Now you could, because here's the thing, with a function like this, the voltage is changing, right? It starts at 0, it goes up to 5, it goes down to 2, right? It could be anywhere. And you could address that with like a piecewise thing, but then you have to do multiple things, and it's a whole thing, right? The way that actually they teach us how to do this, and the better way to do this is something called superposition. All right, now the idea with superposition is we just make a 1V unit step function. All right, so we just do 1 volt, we do that function, and we calculate it for just 1 volt, right? And then once we do that, then we can scale it up and we can scale it back and multiply it times this. All right, and I'll show you what that looks like. So just bear with me for a second. But just know that that's what we're doing, right? We're actually just gonna do a 1 volt unit step for now. And what does that look like? Well, that looks like at time equals 0, right? It goes from 0 to 1. All right, and that's just gonna simplify our equations for now and just make things a little easier. All right, so let's start plugging in. Well, first of all, we need to find B1, right? So how do we do that? Again, our cheat sheet has it right here. B1 is equal to x0 minus x infinity, right? So in this case, x is VC, right? All right, so we already know that VC towards infinity is 1, right? Because of our unit step function. We also know that VC of 0 is just going to be 0, right? Because, again, it's going to be an open circuit over here, which means no current, blah, blah, blah. We already did that in the first part of this question. So we know that's going to be 0. Okay, perfect. Now we need to find, or actually let me just get this down. It's equal to -1. All right, B2, what is B2 equal to? This one's going to be a little bit more tricky. There's our equation right there, so let's write it down. Oops. Okay, so first things first, we already know that this is going to be B1, right? So we can just get rid of this. We can even just replace it with B1. All right, so here's the tricky part. This thing right over here, derivative of the voltage of the capacitor. How do we do that? Well, we could take this whole thing. We could, take the derivative of it. That seems like a lot of work, though. So I'm going to look for a shortcut, all right? And here's the thing. You should keep this equation in mind because this will help you out a lot, all right? Let me just write it down for now. You'll see why we're using it. So I is equal to C dV dt. Do you notice this? Or I see it. Actually, I should say I see, right? If you notice, this equation right here is our current for a capacitor, right? And it shows our derivative of voltage. So it actually has this derivative of voltage right here, right? So why is this helpful? Well, here's the thing, right? Think about DC conditions, right? At 0, at time equals 0, right? This is going to be an open circuit, right? Which means this current is going to be 0. Again, if you want to look back to our table from before, you can even see it right here, right? Our current is always going to be 0. From the beginning to infinity, it's always going to be 0, right? So one thing we know right away is that this current is going to be 0, right? So we just plug in C dV dt, divide both sides by C. Okay, yes, this helps. Why does this help? Because we just said that our derivative is always going to be 0, right? So this whole thing just becomes 0. Perfect. We're almost there. Now, we just got to find this thing, right? This is just going to be negative alpha, right? All right, pretty straightforward. We got our constants. Now, let's plug them all in to our master equation. All right, so let's start plugging in. VC of t is equal to B1, right? -1 minus alpha t, this all times e to the negative alpha t, right? Plus VC to infinity. Again, this thing just becomes 1. All right. All right, this is our equation, our base equation for now. We can even, pull a common 1 out of here. So we can even go like this and say, we can pull a -1 out of here, right? And we can say 1 plus alpha t, right? And then same thing, plus 1, right? Now, what do we do from here? Well, here's the thing. We have our equation for this unit step function, right? So all we got to do is scale this thing up. We just got to do this times our unit step function. What was our unit step function? Well, it's over here. It's this big messy thing over here, right? So let's write that down. All of this times 5ut minus 3t minus, what was it? T minus 5 nanoseconds. There we go. All right. So let's distribute it out. So on this side, we get 5 times, we can even move this one to the front over here because that's how the solutions have it. Right? UT minus 3, 1 minus 1 plus alpha t e to negative alpha t. Okay, here's the thing. One more thing to keep in mind. All right, we're almost there. every time you use a unit step function, always look at the time. All right, this is going to be t minus 5, which means this is going to be t minus 5 and this one. So we actually need to write those in. All right. All right, and then wrap this in our u of t minus 5. All right, and this massive thing right here, well, that's our final equation using our magic equations. And yeah, I'm not gonna move it up here for the sake of because it's the same thing. But yeah, that is how we got here.